What is the biggest problem in deep learning today? Well, everybody seems to agree that the biggest problem seems to be data. And for once, NASA actually has something in common with the little guy on the bottom. The world is at our fingertips. In 2020, we have 35 petabytes of data, and in 30 years, we're going to have eightfold that amount. But what is the problem with this data? This data is incredibly dumb. We have no labels, and we can't make any sense of it. All we know is that we have images. And why can't we just label all the data? Well, the previous presentation talked about this a lot, but it takes a lot of effort to label data. It took 22 years to label 14 million images, and our data set, if we're just going by pure size, is 200,000 times bigger. We are working on a data set of massive scale, so we can't label every single image. And what is the problem with having no labels in the first place? Supervised learning fails when you have a low amount of labels. The way supervised learning works is, for any given input image, it leverages the desired output, what the output is supposed to be, to make sense of what the input was in the first place. So if you take away a few labels, you can't make any sense of the images that you had earlier. Take away more and more labels, you are losing out on this information that you had earlier. And eventually, you are going to get very, very low accuracy. You are not going to do better than random guessing, and you're going to have no understanding of data in the first place. So we're at a crossroads. We can either have our data rot in some service like AWS and make this guy a quick buck, or we can choose to label the data using a service like Mechanical Turk and make this guy a quick buck. Unfortunately, NASA does not have this privilege, and this begs the question, who can best leverage a data set with very few labels? Introducing Celestial AI, a self-supervised pipeline for satellite image classification. This is a project that I've been working on for the past few weeks with Cool, and the biggest improvement in our thing is the art of self-supervised machine learning. How does self-supervised machine learning work? The first step is gaining a general understanding of the data. We ignore the labels that we have and try to get some understanding of what the data looks like. Then we have this model that really understands what makes an image similar or dissimilar. And then eventually, what we do is we narrow this down to the small percent of labels that we actually have. So if we have maybe only 10% of labels, we first do step one on 100% of the images. And on step two, we use on the 10% of images that we do have labels for. So what does this look like? Well, there's actually a very simple, not so simple framework to do this. And this algorithm is SimCLR. And this algorithm came out in January 2020 and is perfect for the task at hand. And it works in the step one, step two dichotomy laid out earlier. Let's go into step one. How can we train on unlabeled images? For step one, all we're doing is giving the model a bag of images, and we're asking it to understand what makes an image similar or dissimilar. And this is quite a complicated task. How can we even do this in the first place? Well, what we do is we first take an image. We don't know what's in the image. We just know that it contains something important. Then we generate one augmentation of the image and a second augmentation of the image. And you can see that these images are going to be pixely different. They're different by the pixel, so the computer is going to recognize these as different images. But as humans, we know that if we take an image and we run it through two augmentations, the content of the image, what's inside the image, is the exact same. We are not changing any properties. We are just changing maybe how it looks like pixel-wise. So we want a model that will identify both of these as similar images. So what do? We run these images through our models. And as Abhigya and Mike graciously explained in the previous presentation, we can get a numerical representation for our image. We can get an image embedding. Now, these image embeddings are going to be different. Since the input images had different pixels, our embeddings are going to be different because our model is not that smart. However, we would like to make our model smarter. So what do? We compare the embeddings at the end and we instruct our model, hey, these embeddings are different, but we'd like them to be similar because we know that we gave you the exact same image. What happens? These embeddings are brought closer together. We have the model learn that these embeddings need to be closer together, and the model adjusts for this throughout. So given two augmentations of the exact same image, it knows that these are similar and it works upon that. The major improvement is for similar images, it learns that they're similar, and for dissimilar images, it'll learn through this process that they're not similar. And this is just a rather fast GIF of how the process works. Let's start at the bottom. We have an image, we run it through an augmentation, we run it through our model, and then we compare the end results. Then we want our end results to be either closer together or farther apart based on what the input was. And you can just straight outright see how difficult this task is. We're giving it different colors, we're giving it different parts of a dog's body. This is a very, very complicated task. So now I just want to highlight how difficult this task is. And to do this, we will be playing Double Jeopardy on the ResISC 45 dataset. ResISC 45 is a dataset that has a bunch of satellite imagery meant for scene classification. So, do these two images belong to the same category? Well, if you look carefully enough, they look like the residential neighborhoods, right? They actually belong to different categories in this dataset. The left belongs to a mobile home park, while the right belongs to a medium residential neighborhood, just outlining how specific the classes are for this project. Do these two images belong to the same category? Well, the right kind of looks like a forest, and the left maybe looks like a play structure, a school, something like that. Well, if you knew what was most important in this task, if you look close enough, if you knew what basketball looked like, and if you knew that color didn't matter, you would notice that these are both actually basketball courts. And this is an extremely difficult task to ask a machine to do. And the final thing, are these two images in the same category? Well, if you look close enough, both of them look like farmland, right? They actually belong to different categories. The left is rectangular farmland, and the right, believe it or not, is circular farmland because every square is composed of 4 circles. So as you can see, this data set is very, very complex, and I wouldn't want to be the human that's labeling this task. So what is our issue? We need to train a model to do this without any labels whatsoever. We're just handing it a bag of images, and it needs to identify that images are similar or dissimilar. And how can we even train a model to do this in the first place? Surprise, surprise, SimCLR works out. So what we do is we evaluate our model on a nearest neighbor task. Given an arbitrary image in the dataset, we ask the model, what is the nearest neighbor? What is the second nearest neighbor? What is the third nearest neighbor? What is the 10th nearest neighbor? And we ask it what it thinks the most similar images are. And what we get is the most similar image has around a 35% accuracy, which is very impressive because random guessing gives you a 2% accuracy on this data set. And this is actually a very small amount of data. When we add a bit more data, when we multiply the amount of data by 4 times, we're getting a 2 to 5% jump across the entire spectrum, which shows that even if you're giving it more unlabeled images, the model performs better. And this is very, very exciting because the actual data set is going to be a million times bigger than whatever small toy data set we're playing with right now. So only imagine the possibilities for the accuracy by just handing it a bunch of images that have 0 labels or 0 understanding of what's going on. And this is just to prove that this is quite a difficult task. So you don't need to completely understand this graph, but it's the same graph as earlier, split by the 45 classes that we have. The top purple line, the highest accuracy that we have, is the desert classification, which obviously it's very easy to identify deserts. They're just the absence of everything else. And the bottom, we have a mix of a bunch of things. For example, we have dense residential, medium residential, and sparse residential all mixed down there. So you can see that this model is not memorizing things. It's learning like a human does and gaining some general understanding. Because if it's memorizing, it wouldn't get confused between these certain classes that are actually very similar to each other. So the next question is, sure, we have some general understanding of what's going on in the data, and that's actually the perfect model to use for the reverse image search outlined earlier. But we want to go a step further. We want to ask, how can we take this general model and use it to get actionable predictions? How can we take this data theoretic understanding of the data and leverage classification from it? This is where we come into step 2, which is the labeled portion of the project. So what we do is consider the blue model at the bottom as the general understanding that we have from the previous task. This is great for telling if 2 images are similar, if 2 images are dissimilar, et cetera, but it's not very good for getting the exact class of the data. What do? We pop on a little head, and these 3 layers at the end of our model are dedicated just for the classification of the actual data. We put these 3 layers to identify, is it a desert? Is it a sparse residential? Is it a medium residential? Is it a basketball court? And these 3 layers are trained upon the 10% of labels, the 1% of labels, the 0.1% of labels that we might actually have. It's trained on this fraction, and it basically takes this general understanding and narrows it down to the actual task at hand. So how does this work? Well, we basically evaluate the accuracy of the model based on the percent of labels that you give. The black line at the bottom is if we just had the model randomly guess. The red dot at the top right is if you gave a standard supervised model, just like no SimCLR, if you gave it 100% of the labels, how well does it perform? Well, it actually performs quite well, like at 80%. But you take away a few labels, the accuracy drops. You take away a few more, the accuracy drops even more. And eventually, the accuracy drops so low when you give it a small enough percent of labels that the model cannot do any better than random guessing. You don't even need to go through this whole machine learning nonsense in the first place. Now, for the big reveal, how does SimCLR perform on this data set? Well, let's take a peek. This is what SimCLR looks like on the exact same task. Now, I understand what you're thinking. At 100% of labels, it's not really that different. If you had the money for 100% of labels, I say go with that. You can ignore the rest of my project. But if you only have $750 that you can spend on something and you're actually NASA, you guys are not going to have that much money and you guys will only be able to leverage a small percent of labels. At a small percent of labels, what happens? Standard supervised can't learn anything about the data, but SimCLR, it can get a non-trivial understanding of the data and it can get a test accuracy of 25%, which is quite impressive considering that you're only giving it like near 4% of the labels. And again, this experiment was conducted on the UC Merced dataset, and the UC Merced dataset is, again, very tiny, like 2,000 images. So SimCLR's best performance is when you give a lot of unlabeled images and very, very few labels. So what you're going to be seeing is that when we expand this to the dataset that NASA actually has, NASA is in the perfect position to leverage SimCLR for their exact tasks and to leverage it for basically reverse image search and to leverage it for classification. Now, what does future work entail? Well, future work entails using this for multi-resolution, multispectral imagery, basically generalizing the model to work for more types of images rather than just RGB. Future work also includes incorporating more recent and more efficient algorithms like SWAVE and contrast predictive coding, which are more recent algorithms that have come out, probably as a result of researchers being cooped at home. And we can also use this exact same model for the reverse image search that we were talking about earlier. So what are the conclusions? Self-supervised learning is cheaper because it requires less labels. Self-supervised learning is more accurate because it's more robust when you have a small percent of labels. And self-supervised learning performs with more data, regardless of if the data is unlabeled or labeled. You can just throw it random images of the Earth and self-supervised learning performance will increase drastically. So at the end of the day, we're all against child labor. So hire children to make models, not labels. Thank you.